Hi everyone. So welcome to supplementary video 8. And this video is basically about an example of finite Fourier transform. And this is one of the practice problems that we suggested you for the exam in homework 2A, which is the ungraded homework. So let me try to walk you through this example. And the idea here is to give you a sort of a slightly different problem of finite Fourier transform. And hopefully that will also give you more practice and you'll get more familiar with the method. All right, so the problem setup is this, that we have a 1D unsteady system. So like it's written here, it's a 1D unsteady system. The x is equal to 0 boundary is at a constant concentration, and even the x is equal to L boundary is at constant concentration, but x is equal to 0 is at C and naught, and the x is equal to L concentration is at concentration of 0. The initial concentration is also given to be 0. Now, if we have this setup, if the length was infinity, you can imagine this becomes the similarity transform problem that we have solved in the class. But in this case, we have not been given that. We have been given a finite length. And the question is to solve for the concentration profile as a function of space and time. So typically what we do in these problems is, of course, we start with the governing equation. So a governing equation of a species balance is del C by del T, and it has been given no convection and pseudo binary. So I'm directly using the equation for pseudo binary systems plus RA, which is where RA is the production term for A. So this is 0 because there is no reaction, there is no convection. So this is 0, and we simply basically get del C by del T is dA del square CA by del X square. So I hope now this is becoming second nature to you. You are able to appreciate this equation. It's just an unsteady diffusion equation, which you get for unsteady diffusion. Now the second thing is to write down the boundary conditions and initial conditions. So boundary conditions and initial conditions. So boundary condition is CA at 0, T is CA naught, right? And CA of L, T is 0. So I'm simply writing the conditions provided. It's very easy conditions, constant value, C naught and 0 at x is equal to 0 and T respectively. And simply CA of initial condition for all x at t equal to 0 is 0. So these are the boundary conditions and initial conditions. Now, the third step is to solve. So typically we solve the problem now. So this is a PDE. This is not an ODE, so we cannot just solve using easier method. This is a PDE. So one of the choices we have a similarity transform, but because this is a finite system and there is no early time restriction provided to us, this is not possible to solve using similarity transform. Then we have a regular perturbation expansion, but there is no small parameter here not provided to us, and we can't reason out any small parameter right away, so we can't use regular perturbation. But we can see this is a linear problem. So you can see that there is only CA here, CA here. This is a linear problem. So this is linear. Plus there are boundary coordinates because it's only x is equal to 0 and x is equal to L. Boundary coordinates. So we will use the FFT method. Okay, so that's the reasoning. So that's the process. The first thing we typically do before we start any FFT steps is non-dimensionalize. And we did the same problem, non-dimensionalization, a couple of times in class. So I'm just directly going to give you the result. Theta is CA by C naught. X tilde is X by L. But I do really encourage you to try this yourself. dt by L square. So it becomes del theta by del tau is del square theta by del X tilde square. Okay, where theta of 0, tau is 1, theta of 1, tau is 0, and theta of x tilde, 0 is 0. So these are the initial and boundary conditions. Okay. So hopefully you're able to follow. We just changed from the time to dimensionless time, dimensionless length, and theta C by C naught. Now we have the initial conditions of 1, 0 rather than C naught 0, and the boundary conditions of 1, 0, and the initial condition obviously being 0 everywhere. Okay. So hopefully this makes sense. This is you can come to this conclusion yourself. All these equations, I hope, are easy to follow now. So when we apply the FFT, we first propose a form. So propose a form of FFT, and to do that, like we have discussed before, we can write this as summation of theta n of tau phi n of x tilde, where phi n of x tilde is the basis function, right? And why did we choose theta in tau and phi in x? Because the boundaries are in x. The finite coordinate boundaries are in x. So that's why the obvious choice of basis function is the x dimension. Now, the second step we have to do is to choose basis function, or rather define basis function. Choose basis function. Okay. So now to do that, we can basically go and look at the table. So this is the table we have been using. So our conditions are theta at x equal to 0 is 1, and theta at x is equal to 1 is 0. So, constant value of 1 and constant value of 0. So if you look at the table, only the case 1 where the values are both the conditions are constant value is there, but it enforces us to use only 0 value. So the value has to be the same, but clearly the value is 1 at the boundary. So from this basically picture, we cannot use the FFT, and we cannot use any of these cases. And that's where the process comes in, that these boundary conditions have all been assumed to be homogeneous, where the values are exactly equal to 0. But sometimes in the actual problem, you actually see the problems are not 0, that there is a finite value, like we have concentration to be equal to 1. So what do we do that in such a case? And this is something we have not discussed in class, but I wanted to make sure that you are aware of this, that we basically use, whenever you see a non-homogeneous system, and you might have seen this, we basically use principle of superposition. Principle of superposition. Okay. And the idea here is basically to simplify our life, basically, and say that we will basically find two solutions and then superpose them. And to give you some sort of idea, what we are basically saying here we'll do is, we'll say theta of x comma tau, theta of x tilde comma tau has two elements, where one element is fx tilde, which is basically not a function of time, and the second part is a function of both space and time. And the reason we are doing this, is because we want essentially to make that boundary condition homogeneous. If it is homogeneous, we know how to solve. So this fx here, this fx part here, is basically trying to help us. It is trying to help us satisfy that non-homogeneity in the boundary condition. So to resolve the non-homogeneity in boundary condition. Okay. So basically, we have to scrap these 3.1 and 3.2 steps. We have to first go back and use this substitution back in the original equation. So now let's go back to the substitute this in governing equation. Okay. So governing equation is del theta by del tau is del square theta by del x square, right? Now I substitute this formula here. Okay, so the left hand side would simply become del g by del tau, because f is not a function of t. So right, I'm substituting theta as f plus g, because f is not a function of t. The left hand side is just del g by del tau. The right hand side is del square f, or rather d square f by dx square, plus del square g by del x square. And you will see that this linearity is basically very important here. So we are able to do this because this is a linear problem. If it was not a linear problem, we will not be able to just add things like that. So this principle of superposition is only valid for linear problems. Okay, so now if this is to be true for any function f and g, we basically can say there are two equations here. One equation is d square f where dx square is 0, and the other equation becomes del g by del tau is del square g by del x square. Okay, so we get two equations now, two equations. Similarly, we have to also modify boundary conditions and initial conditions. So our boundary condition was theta at x equal to 1 comma tau, which is basically equal to 1, and this means f of 1 plus g of 1 comma tau is this value, right? Because theta is f plus g, and we are evaluating at x equal to 1. So what we can force is we can say, oh, well, we want f of 1 to be 1 and g of 1 comma tau to be 0. If we do that, we will satisfy this equation, right? And we will also make this condition homogeneous. Okay, hopefully that makes sense. Similarly, if I have theta, sorry, I made a mistake here. This is not my mistake. This is not x equal to 1. This is all x equal to 0. Sorry about that. Just correct this. Hopefully this makes sense, because it's not f of 1. This is all f of 0. Sorry. Let me correct this. I'll explain this again. Okay, so we had the condition, we had the boundary condition, this one, right? So I'm basically saying the left hand side is now f plus g. So that's why theta of 0 comma tau is 1, and this is f plus g. And so we basically are choosing it to make it homogeneous. Okay, so, and you're not violating anything, because we can see if we substitute, if we satisfy this equation, the sum will naturally satisfy this equation, right? So we are not violating this. And this may seem sort of almost arbitrary, but this is a very common practice whenever you have a principle of superposition or a linear problem. So that's why we chose this problem, to kind of give you a bit of a different flavor, that sometimes you have to decompose a problem into two parts, one which only has this x dependence, and that is to satisfy the non-homogeneity. Okay, so the second thing is when you have x equal to 1 comma tau, so this is equal to 0. Okay, this is equal to 0, and this is again equal to f of 1 plus g of 1 comma tau is equal to this value, or simply here we can choose both of them to be 0. That's how we can get this to be homogeneous. Okay, so now what we have been able to do from the boundary conditions is that we have basically essentially defined the condition for f completely, right? The f, because f is only a function of space, we don't need time. So now we can substitute for f with the two boundary conditions and then proceed to g. Okay, so let's start with f. So solve f first. Solve f first. So it's d square f by dx square is 0. And f of 0 is 1. And f of 1 is 0. Okay, and this essentially means f becomes a1x plus b1. And you can, I invite you to sort of substitute this. Essentially, what you will get is it should become a1 minus x. You can verify this. This is what you'll get, that when you substitute the value, you'll get f is equal to be 1 minus x. And this makes sense because the value is 1 and the value is 0, and it's a linear function, so it should be 1 minus x. Okay, so we get this. Now that we have f, and now we have determined f, now we can go back to the initial condition, which basically said that initial condition said that g of x comma 0 is equal to 0. Right? We know this, g of x comma 0 is equal to 0, or f of x plus g of x comma 0 is equal to 0, or g of x comma 0 is equal to minus f of x, or g of x comma 0 is x minus 1. So now I will shade these parts, which are this one, and this one. So these allow me to evaluate the boundary conditions and initial condition for G. And you look at the equation for G. G is this equation, which is very similar to what we had, but now our boundary conditions are homogeneous, right? Because our boundary conditions are simply both of the values are 0. So by breaking this into F and G, we essentially resolve the non-homogeneity, and by basically uh, making sure we are also satisfying the initial condition, we have incorporated this addition into the solution by transforming the initial condition to x minus 1 for G. And initial condition we can handle, right? So essentially what happened here was we started with the substitution of theta into phi n. We saw that it cannot work because of non-homogeneity. Then we said we'll break it into two parts, f and g, and for these functions to be valid, they have to go to 0 independently. And when we did that, then we can see one problem becomes an ODE, the other becomes a PDE. ODE is easier to solve, but for ODE, we need boundary conditions. So we went back to the original boundary conditions and we created these boundary conditions to make the system homogeneous. Once we did that, we got the result for F, and then we now also got the initial condition for G. So now my problem essentially becomes this. So my problem becomes del G by del tau, is del square G by del x square, and G of 0 comma tau is 0, which is the boundary condition which we created. G of 1 comma tau is 0, but G of x comma 0 is x minus 1. So this is because we also have when we have a theta, which is 1 minus x, we want to make sure we are accounting for that in the initial condition. So now we will basically apply FFT on this. We'll apply FFT on this. Now, because the boundary conditions are homogeneous. So this is sort of like the complicated portion of the problem, is that you cannot directly use FFT. So we artificially created this problem to apply FFT. So essentially now we'll go back to the steps. Now let's go back to 3.1, which is apply on G. So we'll say G is something like theta n of tau phi n of x tilde. Then phi n of x tilde, we can go back and again look at the table, 0, 0 value, which is the first case, and L is 1. So this again becomes root 2 sine pi, sine pi x tilde, right? 3.3, modify governing equation. So modify governing equation. Now our governing equation is this. So modify governing equation. So we have del G by del tau is del square G by del x square. We'll basically make it del G by del tau phi n x tilde dx. 0 to 1 is del square G by del x square phi n x tilde dx. 0 to 1, multiplying, right? And I think you can all verify this, that this basically becomes dg d theta n by d tau on the left hand side. Here we get the same del theta by del x phi n, sorry, del g by del x, not del theta, my mistake. Del g by del x phi n minus d phi n by dx g 0 to 1 minus n pi square theta n. And again, because the system is homogeneous, this boundary terms will cancel out. Please do verify this. And finally, what you will get is the equation d theta n by d tau is minus n pi square theta n. Okay. What we need now is so fourth step is to get the initial condition on this theta n. So this is important, that theta n of 0 is 0 to 1. Now we have to be careful, it is g, not the theta, because we are applying now on this equation g of x comma 0 phi n x dx. G of x comma 0 is x minus 1, and phi n of x, phi n is sine root 2 sine n by x dx, right? And what this comes out to be, and you can verify this, again, you can put it on Wolfram alpha or stuff like, any of the computations you like, you'll get it to be minus root 2 by n pi theta n of 0. Okay. Or simply, this means 3.5, or sorry, theta n essentially from this here, you can find that this will be minus root 2 by n pi exponentially minus n pi square tau. Okay. So we found the g. So now we found the g. The g essentially here becomes g of x tilde comma tau is minus root 2 by n pi exponential minus n pi square into tau times sine of n pi x. But now for the value of theta, finally, for the value of theta, we have f of x plus g of x tau, or 1 minus x minus root 2 by, sorry, actually this is not root 2, this is 2. I keep making this mistake. Sorry about that. And this is minus 2 by n pi, and this is, there is a summation 2. So this is another error I do commonly in the class 2. So there is a summation minus n of 2 by n pi exponential minus n pi square tau sine of n pi x. So this was a very long solution, I realize that, but I hope this kind of gave you a flavor of what we do when the system does not allow us to simplify the system. So let's walk through this slowly once to make sure. So we were given a problem, constant concentration of CNR, 0 from 0 to L, initial concentration to be 0. Pseudo binary, 1D unsteady problem, no convection, which gave us the governed equation, and we had the boundary condition and initial condition. Because this was a linear boundary coordinate problem, we could apply FFT. When we non-dimensionalized it, we got a very simple equation, del theta by del tau is del square theta by del x square. And we had, boundary conditions of 1, 0 and initial condition of 0. Now, when you propose the form and when to choose the basis function, we saw that there is no case which allows us to choose the boundary conditions we have, because there is a value of 1 floating around at x is equal to 0. So to do that, we basically said we will apply this principle of superposition. We will create another portion which is just dependent on x and not dependent on time, so that is able to kind of circumvent this non-homogeneity in the boundary condition. So we substituted f and g back in the equation. We got two equations because they have to be independently, they have to independently hold for this system to be, for f and g to be valid. Then we split the boundary condition, and we chose the boundary conditions in a way so that we can make the g, which is a function of x and tau, to be homogeneous. It was simple enough to solve the ODE because f is simply an ODE system. We created an ODE in f, we solved for f. Then from that, we could calculate an initial condition for g, so that theta still is 0, even if f is 0 and g is non-zero for given values of x at time t equal to 0, the sum is still 0. With that, we applied FFT on g. We started with the new form, theta into phi n. We had the phi n simply root 2 sine pi x. Then we modified the equation, and we used the g's initial condition to calculate theta n of 0. And then we got a final value of g, and then we finally got the final value of theta. So this is a very long method, but this allows you to circumvent the problem of, whenever you have a non-homogeneity in the boundary condition. So I do recommend you to try this yourself and convince yourself that you can actually solve this. Another interesting thing is you can verify by putting tau equal to 0, for instance, in these things, and see that you can actually get the initial condition to be 0. You can put x is equal to 0 in this problem. So for instance, if you put x is equal to 0, you will see that you will get theta equal to 1. If you put x is equal to 1, you will see that you will get theta equal to 0. So you can verify initial and boundary conditions by substituting in the final result to convince yourself that linear superposition works. So I hope this video was useful. Feel free to write to me if there's any confusion, and I look forward to seeing you in the next video.